The model of the atom in the late 19th century was very simple. Atoms were hard, solid spheres with protons and electrons interspersed throughout. This was known as the plum pudding model, and it's shown here. To show why it was called the plum pudding model, here is an actual picture of a plum pudding. You'll notice the resemblance. Rutherford's discovery that most of an atom was empty space with a densely packed, positively charged nucleus was a revelation. Shown here is the basic model. Here we have the nucleus, which is filled with protons, and the rest of the atom is composed of electrons. However, there was much still to be addressed about atomic structures, namely, what was it about the electrons that made elements different? Three main observations still required explanations: blackbody radiation, the photoelectric effect, and atomic emission spectra. We'll address blackbody radiation first. It was well known that heating metals to a sufficient temperature caused them to glow or emit light, and so metal was said to be red hot. The hotter the metal, the whiter it glowed, and it was said to be white hot. So the question is, why would metals emit light, and why would the colour of that light be dependent on the temperature? To answer these questions, we must first consider blackbody radiation. Blackbody radiation refers to an object that absorbs all the electromagnetic radiation, such as light, that it strikes the object and re-radiates that radiation. A true blackbody is hypothetical, but our hot metals, like the lamp filament shown here, will serve as imperfect examples of blackbody radiation. Measurements on these hot objects indicated that the energy emitted at a certain temperature depended on the wavelength of the emitted radiation. Notice here how the intensity of the emitted radiation changes with wavelength. Also note, the hotter the object, the greater the intensity of radiation and the shorter the wavelength. Thus, there existed a relationship between energy and wavelength. Max Planck postulated that not only was energy related to wavelength, and hence frequency, according to these equations, where E equals energy, H equals Planck's constant, C equals speed of light, nu, which is the frequency, the squiggly v, lambda is the wavelength, but that this energy was quantized and existed only as whole number ratios according to the equation shown here, where n equals 1, 2, 3, 4, 5, 6, and so on. You can think of quantized as something which occurs only in fixed amounts, for example eggs. Hens can lay only one egg, or two eggs, or three eggs, or four eggs, or so on and so forth. But no hen can lay a half an egg, or 1.5 eggs. Planck's discovery of the quantization of energy led to Einstein's explanation for the photoelectric effect. So what is the photoelectric effect? Back when Planck, Einstein, and all the other physicists were pondering these problems, it was known that shining light on certain metals led to the ejection of photoelectrons. This ejection of photoelectrons depended on the wavelength of light. Above a certain wavelength, there was no ejection, but below that wavelength, there was ejection of photoelectrons. Remember that energy and wavelength are inversely proportional to each other, so as wavelength increases, energy decreases. The intensity of the light shining on the metal had no effect above the certain wavelength for that metal. No matter how bright the light, no electrons were ejected. However, below that wavelength, the brighter the light, the more electrons were ejected. Planck's idea of quantization allowed Einstein to propose that for the photoelectric effect to occur, a minimum energy, or threshold energy, was required. That's why the effect only occurred below certain wavelengths, or energies. Furthermore, Einstein postulated that the incoming light acted as if it were packets of light, or what he called photons. In other words, light had particle-like properties. Photons hitting atoms knocked out electrons if they had enough energy. So that explains why the more intense the light, the more photons were hitting the metal surface, and the more electrons were emitted, provided that the photons had enough energy to begin with. So to summarise, as far as atoms are concerned, energy is quantized and occurs in whole number ratios. Furthermore, electron movements are also quantized. This leads us to consider emissions. Every element, when subjected to a high voltage and atomized, will exhibit a different colour of light. Hydrogen, shown here, is pink under these conditions. If that light is shone through a slit, followed by a prism, the light separates into different components. So hydrogen produces 4 lines in the line spectrum: a purple one, a blue one, a green one and a red one. The observed lines always occur at these wavelengths. After much trial and error, Balmer was able to derive the relationship between the lines. The relationship was described by this simple equation. N in this case is equal to 3, 4, 5 or 6. The discovery of more lines out with the visible region led to the more general equation shown here, where N1 and N2 are always whole numbers, or in other words, electronic transitions were quantized. Note that the equations shown here are only applicable to hydrogen or 1 electron N. The diagram shown here summarises what we have now learned about the quantization of energy levels and demonstrates why an atom releases energy in the form of electromagnetic radiation. All of this brings us one step closer to a better model for atomic structure.